Hi, everyone.
Hello.
Hello.
Okay, so good afternoon, everyone, and thank you for coming to our WMG Steel Group Colloquium. Today we have a great speaker, Dr. Begonia Santillana from Tata Steel, Netherlands. So I take a couple of minutes to introduce Begonia to all, and then we can proceed with our talk. So Begonia graduated back in 2002 as a metallurgical engineer at University Technological National in Argentina. In 2013, she received PhD from Delft University, Netherlands, and her PhD title is Thermo-mechanical properties of steel during solidification. She is currently working as a principal scientist in the field of thermomechanical properties during solidification of steels. People are coming 1 second. Yeah. Complementary to Dr. Santillana's research, she also supervised several PhDs and MSc students and regularly gives guest lectures at different universities worldwide. She has published more than 40 peer-reviewed publications and is a regular reviewer for several journals and for the research program of the European Union. She has co-authored the 2013 IOM3 Williams Award manuscript and 2017 AST Jerry Silver Award. Begonia is also a member of the Materials Chemistry Committee of the IOM3. Today, Begonia is willing to present an overview of casting and solidification research at Tata Steel. And thank you, Begonia, for accepting our invitation. And thanks for your time. And I request you to present your talk now.
Thank you very much. Thank you, Prakash, and thank you for inviting me, in fact. And I will share my screen. So if everybody's seeing it, so then I will put it in present mode.
Yeah.
In the preset mode, I don't have any view of you guys. So if you have a question or something like that, please just ask. Just raise the question and unmute yourself and ask. And well, like Prakash said, I would like to present you today a little bit of an overview of some or the most of the casting and solidification research we have been doing. And I said we because luckily I don't do it myself. So here I would like to thank also to many people who have contributed, and they do contribute on a daily basis on all the fantastic research and all the good results we are getting on our research in Tata Steel R&D. But before a little bit for the people who do not know me and do know a little bit of Tata Steel, I would like to introduce our group. I work in R&D and the organization at Tata Steel in the Netherlands. Currently, we have about 300 people working, where about 33% is on the sector, on the processes, on sector, so directly related to the product. We have the majority of it. And then we have some people and some program working on corporate research, and there is a little bit of direct business support. We have, there are 6 departments, and the department where I'm working is iron making, steel making, and casting, obviously. And we have one European technology program organized through a matrix organization. When I say European, is the Netherlands, actually. A matrix means that we are organized in knowledge groups, and there are projects defined, and the projects required or request different skills or different expertise along all the knowledge groups or most of the knowledge groups. Therefore, it's a very integrated organization. But that's not all. We also have within R&D 2 internal services who support our research, and it is one of them is the group of intellectual properties, where it helps us for patent applications and patent oppositions and everything that is related with IP. And also our library and knowledge and library services keeps us on schedule and regularly send us a lot of updates for a lot of new papers, new publications, and also conferences, etc. It's everything standing there. We do not do everything alone, so we do broadly collaborate with universities, institutes. Sometimes we also collaborate with competitors on a project basis, for example, on RFCS projects. This is, across knowledge groups and across universities, institutions, and so on. You only win and then you only enhance yourself, and thus you enhance the research. We have collaborations within the Netherlands with most of the universities in the Netherlands, but also in the UK. Yeah, Warwick and Swansea are very keen partners to collaborate with us. However, it does not all. We also collaborate outside Europe. For example, with the McMaster Consortium, with USTB in China, and the Continuous Casting Consortium in Colorado School of Mines. There are other research centers where we are taking part of, and we are part of it, and partners like CRM and MPI in the UK, which are the most dominant partners when we have other research centers to collaborate. Last but not least, we have the RFCS projects. However, in the last few years, the RFCS itself, the budget has been very, very low. So the rate of getting a project approved is very low. But you never lose the hope. A little bit how our existing process route in the Netherlands is. We have 2 blast furnaces, and the hot metal is delivered in torpedo cars. And this hot metal is first desulfurized. Let me see if I can get my pointer. Laser pointer is better. So we first desulfurize it in the desulfurization stations. Then it goes and it's mixed with some scrap in the converter. We have 2 ladle stations, and we have to prepare the ladles, and then we have 2 stirring stations, a vacuum degasser, and 2 ladle stations for alloying. Last but not least, which is the part where I'm, let's say, what I'm gonna focus today is on our casters. Here there are only 2 casters for slab casters. There are only 2 casters drawn in this picture because it's a little bit old, but we have actually at the moment 3 casters. The new caster has started in September 2021, caster 23 we call it. But we have also a thin slab caster, which is a caster with 4 thin slabs, which is directly, the slabs are cast, reheat in a homogenized temperature in an oven, and directly rolled afterwards. There is a little bit, and in this overview, I wanted to show you what is the past, present, and future of solidification research. And before that, I would like to explain you a little bit of some interesting concepts. We find it as a key concept for solidification and casting. The solidification of a steel will be really a fingerprint that marks many of the properties on the final product. Moreover, if a steel cannot be cast, if we design a steel or a composition, if it cannot be cast, it will never be a final product. And the question is not if we can cast a steel, but how can we cast it? So I am a strong believer that there is almost always a way, almost always a process that you can cast a particular composition, but how are we going to do it? And your selection of which process, that's your choice. For that choice, nowadays there are tools, mathematical and physical models, available to help on understanding and to make a choice on the process parameters. But these tools are really widely used. We are obviously not the only ones using them. And they all help you not only to understand the actual process on troubleshooting, but also on designing new steel grades. But you know what? Model needs material properties. And also, let's not forget that the thermomechanical behavior of steel depends on each steel grade. So the chemical composition of that steel grade, it's very important, and it will mark many of the thermomechanical properties. Moreover, there is a mechanical effect, and the formation during a process, during continuous casting, it's very dependent on the process itself, on the process parameters. If we focus a little bit on the casting and continuous casting, basically we have two regions. We like to call the first region is the mold region, so where the steel starts to solidify, the slab is born, and the solidification range, or at least the temperatures we handle at this point or in this stage, they're rather high. It is normally between liquidus temperature and solidus temperature. Both of them, the liquidus and the solidus temperature, could vary a lot depending on the steel composition. And on the mechanical side, here is where we have the first ductility trough, and it is considered to be between 0.9 to 0.99 fraction of solid. Again, it's very dependent on steel composition. The second region is the secondary cooling region. This one has a much broader temperature, and it's more or less between the 1300 that it exits the first region up to about 700. Below that, it's not normal. It could happen, but it's not normal in continuous casting because the steel becomes too stiff and too cold to be able to move it and to further process it, or at least to extract it from the machine. However, let's do not forget that this semi-solid region, the mold region, it will be also in this secondary cooling region, as long as we have a liquid core, we will have a semi-solid region as well. So let's not forget that this region is not that like it stops at mold exit, but it goes on as long as we have liquid steel. No, this didn't go that good. The two regions for research, if we focus again on the mold region, or at least in the semi-solid region, what do we need to research to understand that region, to explore for new steels, for example? Well, first of all, we need to simulate the cracking and the continuous casting conditions. That's very important because a defect in a product, it will never be solved. But moreover, we need to understand the solidification, particularly of new steel grades. There are very advanced high-strength steels and ultra-high-strength steels. They are extremely challenging, not only because of their chemical composition, but mostly because of their complexity. And that includes also, for example, precipitation. What we have internally and in Tata Steel, well, we have something I will show you later. Is called the Mould Cracking Simulator. We have a thermodynamic software. We have Thermocalc, and we have Micres, which is a microstructure phase field simulation software. We also have a wedge mold, which is a static ingot casting, and we are at the moment using it for analyzing segregation and the solidification itself. What we do not have, well, we do not have a way to measure certain material properties. We do not have a glibble. We do not have any kind of Bridgman or solidification lab tests. In the secondary cooling region, Well, again, what we need. In this case, not only the solidification is important, but we need to understand the effect of the process parameters or the casting parameters in the product and process interrelation. We need data. This is much more important in this region to have data on the thermomechanical properties. Why? Because the temperature range is broader. There's much more complex. A lot of more things are happening here, like precipitation, phase transformations, that we need to have a better idea here. What do we have? Well, we have something to measure these thermomechanical properties, a little bit at least, which is based on the datometries. We have, again, the same kind of softwares, and we have a simplified finite element model. What we do not have, the same. We do not have a way to measure material properties. However, you need to understand that for us, it's rather difficult to have a way to measure material properties and use it regularly. Think on one single steel. If you have one single steel, you would need to measure, to understand this steel, you would need to measure it every 10, 20 degrees, maybe 50 degrees. So one single steel will request a list of 20 to 50 different tests to understand it, because you will need to do it along the whole temperature range. If you do those 20 to 50 tests, you multiply it by the 130 different steel grades we have listed on our product list that we sell it commercially. Well, you know, I still have 20 years to go before I go to pension. I don't think I will have enough time to evaluate them all, really. But why? Why we need the modeling and solidification lab tests? First of all, we have CALPHAD, so calculated phase diagrams. And what is the relation with steel making? A long time ago, a very simplified way was the carbon equivalent formulas. So you had a way with a simple formula. It's still used, by the way, on a daily basis. It was a way of seeing what would be the effect of other alloy elements rather than carbon, as if they would react in the way that carbon would react. So also because it was easier to have the carbon phase diagram. So this is like seeing in black and white, really. If you would have gone to 16 colors, let's say, you would have ternaries and quaternary diagrams. However, probably the most used way nowadays is when you are with some more colors, 256, with a thermodynamic software. So when you have complex systems, you just cannot simplify everything in black and white. You really need a broad range of understanding. So phase diagrams, you know, you can calculate a lot of things. Nowadays they are fantastic programs. They are fantastic softwares to calculate either phase diagrams or at least these phase fractions, which is much more useful than a single phase diagram or a pseudo binary diagram. However, the calculations are done on equilibrium. You could use child, but it's the extreme. The reality is really in the middle. It's really between equilibrium and child. But then sometimes you need something that tells you about the precipitation, the precipitate composition for each steel. You could also calculate it with Thermocalc or with any thermodynamic program. However, it's a simple method. It is good enough. It's not bad at all. It's much better than a carbon equivalent formula. But you need kinetics. So there are some limitations that, you know, you have to be aware of. But just remember, going from a black and white and a simplified iron carbon system to a multi-component system is not easy. And not only to do it, to calculate it, but also to understand it, particularly on a daily basis for steel makers. Again, the question is not if we can cut the steel, but how can we cast it? And I will show you how thermodynamics are helping us or have helped us to understand the steels. Kinetics, again, you need some kinetics for the precipitation, but with an equilibrium, you are good enough. We know that when you have high strength, low alloy steels, that are steels known to have microalloyed elements. Why micro? Because are alloyed on a very small amount, so micro scale. So sometimes it's boron, for example, is at the levels of ppms. So they have very, very little amount of these elements in the composition. But this very, very small amount of elements affect broadly the ductility of the steel. And it is very well known that even though they are beneficial because we add them on the composition to improve the final properties of a product, not for nothing. However, you have some disadvantages that during processing, they are known to have a ductility trough. I explained before that the first ductility trough, it happens at the semi-solid region. But then while cooling, you have a second and sometimes a third ductility trough, or even an overlapping of several ductility troughs, depending on the precipitation, depending on all the processing and all the phase transformations that are happening due to the chemical composition. But what happened? Why we are interested on this? No, well, if this precipitation happens, so if you have a ductility trough, it means that your steel is less ductile and it could even crack if it exceeds a certain stresses during casting. That point is very important because that it happens depending on the precipitation of the steels, either at the bending or at the unbending of the continuous caster. Here are some examples how the cracks look like. And on a slab, they are normally transfer cracks. So this is the casting direction. So the cracks will be like this here. This is on a corner crack. But eventually, if I don't see these cracks and the product is rolled, it will look like this. Well, this steel was certainly not meant to do serrated knives. Really not. And so this is not something that we want to sell to our customers. In the example, so what happened? We have a chemical composition, it's somewhat peritectic. We have quite some manganese. Aluminium is done for the deoxidation, but we need to take it into account also because at least a quarter of the aluminium added, even for the deoxidation of the steel, it could bond with nitrogen because we have quite some nitrogen. This is on ppm level. And then we have some niobium and titanium in this steel. So let's use thermocalc. Let's see what we get in a phase fraction versus temperature phase diagram. If I zoom in on the areas where these precipitates are starting to appear, so thermocalc, it's very flexible, but we need to understand what is happening here. Thermocalc says, well, each precipitate is a new phase. So that's how it calls it. So for us, it's a precipitate. So indeed, if you would see the microstructure, you could consider it a new phase because it has a different crystallographic structure. But depending on their composition and their affinity, and temperature obviously as well, this is equilibrium again, they will appear at different temperatures. So if I see here upon cooling, the first precipitate to appear will be a titanium carbonitride. The second one to appear, it will be a niobium one. And last but not least, aluminium. Aluminium nitrides, they will appear as well. But what happens if we want to try to see, to understand the composition of these precipitates, or at least what is happening? Is a carbonite, is a carbide? What is it? So what we can do is, again, ask Thermocalc to give me the phase fractions, or at least the different elements on each phase. In this case, what is plotted here is nitrogen and carbon. Again, the same precipitates. Again, only niobium, aluminium, and titanium. Carbonitrides, aluminium, we know that it's going to be aluminium nitride. So here we have it. It's only aluminium nitride, and it has only aluminium and nitrogen. Obvious. However, if we follow, for example, the titanium one, at the beginning, this little guy likes to form mostly as a nitride. However, it has a sort of a component, or at least a part of it, it will be a carbide. But when the niobium one appears, and that this one on the opposite, it likes to form a carbide and not a nitride, it will fight together with, for the titanium, for the carbon, but not much. However, when the big boy comes, aluminium nitride, it says, no, I want all the nitrogen for myself. Therefore, it's taking out the nitrogen from the titanium and taking it for himself. Yes? Was there a question?
No, nothing.
No, I think so.
Please carry on. Yeah.
So, you know, this, it seems very complex, and what do I get here from? What we get here is the complexity that we cannot get from a simple carbon equivalent formula or a simple phase diagram. We need to go deeper and try to understand all these interrelations. If we know when these precipitates appear, at which temperature, and what is more or less their composition, combine that with an FEM model of the temperature of my slab, what we can do is to know exactly which areas we should avoid, or at least which temperatures we should avoid when we are at the bending and unbending zone. So if we avoid those areas, we are avoiding the areas that most probably they will be in the ductility trough. Therefore, they are most prone to cracking. And therefore, if I avoid those zones, those temperatures, I avoid cracking. So simple is it. From that example, from that particular case was done for one of our casters in Tata Steel, India. And based on that, we have redesigned together with them, knowing all that information, collecting all that information, we have redesigned the cooling of the caster. So in order to reduce the cracking susceptibility. Now, results are speak by itself. If we have, if we add this, the cooling, the dynamic cooling, as we redesigned it, we don't have any cracks. If we have the old cooling, we have a lot of cracks. So the result speaks for itself. Another short example, which is quite interesting example, it's when you have an advanced high-strength steel with boron. Boron is on the levels, again, on ppms. Could be 20, 30, even 50 ppm boron. But it's ppm level, so it's very, very low amount. However, boron, it's an element that it highly influences the solidification of the steel. And why is that? If you have boron in combination with manganese, it could broaden widely and extend enormously your solidus temperature. Up to the point, like in this case, Thermocalc says we have it up to close to 1300 degrees. So we have a huge solidification range. However, be careful, because the last part, the amount of liquid temperature you have is very little. You could say it's very little, so it's okay. In some cases, it's okay, but in other cases, you have to be careful, because this temperature, this very little liquid phase present, it could be present in between grains that are already solidified. Therefore, you could have cracking or even bleeding, like in the case of the photo, because there is not enough strength, or those solidified grains are surrounded by a liquid film. Therefore, they do not have enough strength to hold, and they will bleed. The boron steels, they have also something very, very funny, and it's a not very well known transformation, and it's called a metatectic transformation in a phase diagram. What it happens is it's exactly the opposite. This transformation is exactly the opposite. So like turning upside down, a peritectic transformation. So in a peritectic transformation, we go from two phases, which are a liquid and a solid phase, and we transform to another third phase, which is also solid. In this case, it's the other way around. We are from one phase that is fully solid, we transform to another phase, another two phases. So from one, we go to two phases, and those two phases, one of them is liquid. So what happens? Practically, everything has solidified, and suddenly you have liquid again. Luckily, a lot has been studied, not only from us, but also on the world. There are lots of publications about this metatectic transformation on steels alloyed with boron. But here, nicely enough, also Thermocalc, or a thermodynamic diagram, it shows us the different liquidus and solidus temperatures, because you will have two liquidus and two solidus temperatures in this case. So you have the first one and the second one. In this case, I'm just plotting solidus temperatures, but you have two of them. You have to be aware of that as well. What's the next step for modeling? Well, as I said, from 256 colors, we could have millions of colors. And the millions of colors, it's approachable in the way of modeling. If you go from a simple equilibrium or simple kinetics phase diagrams or thermodynamic software towards, for example, phase field. Phase field is a fantastic tool, fantastic program to simulate many, many things on solidification, because you have not only the phase diagrams and all the thermodynamics, but also you have kinetics, and you could have even fluid flow. But what kind of tests do we have, or we have explored for understanding the steels? Because models, very nice, but they are very idealistic. So what do we have? One of the nicest things we have done is together with Katerina, she did a PhD with you guys in WMG, and she did in situ observations of the solidification, focusing on peritectic steels, hypoperitectic and hyperperitectic steels. I will not go into the details because else I could talk forever, really. Come on, guys, it was a whole PhD. But the fantastic thing was fitting a thermal imaging camera in the confocal microscope. With the thermal imaging camera, she could follow temperatures of the steels and shrinkage of the steels differences during solidification. Why is so important to understand that? Why is so important, particularly why we did focus on peritectic grays? Because while we cast, peritectic grays are very prone to shrinkage. The shrinkage is associated, or it happens because of the phase transformation I explained just before, the peritectic one. So you go from two phases, one is liquid and the other is solid. You will go towards a third phase, which is another solid phase, and the crystallographic structure of that phase is much more compact than the other one. Therefore, there is a shrinkage at the atomic level, at the crystallographic level. That is seen in our process on the shrinkage during solidification of the whole steel shell. It's a very local process. It's very localized, but we are still seeing it like patches, like in this case here. This is a temperature image of a thermocouple lines where the dark patches is shrink. The steel shell has been shrunk and detached from the mold. So if the steel shell shrinks and detached from the mold, what happens? It doesn't extract its heat. If it doesn't extract its heat, it cannot solidify or further solidify. So it cannot further grow as a shell. And thus, also associated to that, because here it has another temperature than here, we will have also thermal stresses, very local between this area and the other area whom is attached to the mold or is touching the mold. Because it detached, it cannot solidify properly. What we get if you take out a steel shell and you scan it on its thickness, what you can see is that the thickness is not even. So that's really not good news, because it could have a lot of thermal stresses, but also a lot of imperfections, and it could even lead to cracking. So a test on a lab scale, it gives us so much information directly related to a process parameter and a process defect that is very, very, very valuable information for us as industrial partners. Another method, because you could say, yeah, okay, thermal is very nice, but we also need some sort of mechanical. So together with the University of Science and Technology, Beijing, USTV, we have two methods that we have been explored. One is a simple directional solidification and quenching, sort of a Bridgman furnace. And the other one is solidification and quenching, so a dropping method of a sample, dropping it into a temperature. The first method, the Bridgman's furnace, it's very well known. So it's directional solidification. We could follow the microstructure. Why is so important that if we follow the microstructure, knowing and quenching it at a certain moment, we can directly relate that with different important temperatures related to our solidification or to the solidification of a particular steel. So the samples is small, but with this directional solidification, also if we could sort of quench it and cut it in different slices, we could also follow how the segregation or how it has been solidified and has been liquid and solid phases has been so important appearing here. So if we use the second method, the solidification and quenching, what happens? We heat up, we melt the sample, and then we drop it, cool it down, either in oil or in salt water, to directly cool it down and quench it. We follow it. We try to follow it also with thermocouples in order to see if what we have set up in the system is what we really get it, right? Because else we don't have any way of following it. And it is very, very accurate. And only a few degrees that we have in the quenching. How does it look like? If we quench it at, so if we take out one sample and quench it at different stages, we have different microstructures. With a simple image analysis, we could say the areas in between those dendrites, we could relate it to a liquid phase that has been very fast solidified compared with the solid phase that was solidifying during this quenching. We can follow the liquid phase fraction from this high temperature to this low temperature for this particular steel. If we combine that, and we use again the same samples, and we go to an EPMA and map it, and then we try to understand the segregation of the different elements, in this case was manganese and silicon, we could get even more information. Knowing, for example, for a simplified thing or phase field diagram, phase field approach, that there is between the solid and the liquid an interface that is, let's say, in between. That interface, also for phase field, this is a very important concept, it could have a different segregation. So if we see it and we follow these two for manganese and sulfur and silicon, excuse me, and again we go for all these temperatures and combined with what we said before, the fraction of solid, we could have an average concentration. Comparing that with shale and equilibrium, we have a very good, accurate relation between what we have been calculating with the phase diagrams or with the thermodynamic software. In this case, again, Thermocalc. Yeah, this is the software of choice, really, for most of us. But we have a very good agreement between what we have been measuring and what we have been calculating. So what it says is, we can trust what we can calculate because it's quite accurate with some measurements. That's a very important concept. But why we do all this? Why we are going to the whole thermodynamic evaluation, the whole phase field approach, and all those painful measurements and tests and everything? It's just simply because segregation is that fingerprint from the solidification that will mark many, many final product properties. Moreover, many defects on the product that will be directly associated to segregation. I have some horrible examples here. They look horrible, really. One example is here. For example, this is deformed and it has been cracked. Another example here, after forming, we have all this border that has been cracked on the same direction here, with all little cracks due to segregation. How bad can look like segregation? Well, it could be look like this bad. The differences in colors between here and the whites and the grays, this is segregated areas and non-segregated areas. This is a welded tube, part of a welded tube. In this case, is on a quarter band where a crack has been associated to highly segregated areas. And in the middle of the tube, moreover, or the strip itself, moreover, the central segregation is seen. So if we connect this with another area who has not segregated at all, the unevenness is what it makes this even more obvious. Moreover, here, for example, another example of a wheel, while forming it, making it, it has opened like a book, really. And this is associated to central segregation. So the strip itself has opened up in two. Well, honestly, I'm not sure about you guys, but I don't want to have this in my car. I don't want to drive a car with this kind of wheel, really. So I want a better one. That's why we do it. Another method which also has been done with another student from Warwick University, it's the wedge mold. We had a static design method of an ingot with different thicknesses to stepwise to measure different solidification or heat extractions on one single sample. Why is that? Because if we have a new steel and we have several choices of casters, I already explained we have 3 slab casters and 1 thin slab caster. Sometimes a new steel, we don't know where are we going to cast it, or if it's even able to cast on all the casters. Could be, but we have to make a choice. Therefore, this is a very good approach. Why? Because in one single sample, one time only, you have in step 5 and in step 3 the different casters. So step 3 will be very comparable to the thin slab caster, and step 5 will be to our slab casters. How we did it, we have done a very nice combination between a heat transfer model and this test of analysis and the analysis, moreover, of the microstructure itself. We know also the primary and secondary R spacing of the dendrites. It's directly or indirectly related to the local solidification and the local cooling conditions. So in one step only, in one ingot, we can have all that information. Moreover, we have this. So we could even take samples for segregation, micro and macro segregation, and analyze it in the lab. So with 25 kilos only, we have a lot more information than if we would have had to cast it with 325 tons of steel. Moreover, why is so important to know that? Because we need to understand what is the effect also. That was a static method, but we need to understand the effect of the fluid flow. Arunava has done, also has built his own model of a single dendrite and the effect of how that dendrite has grown based on a macro fluid flow. So not the fluid flow directly related of the segregation of the dendrite, but the macro fluid flow of filling of the caster. So, and related to that, going back to a slab caster sample, if we know this information, how that dendrite bends following the flow, we could also relate in a very simple slab caster sample how our whole macro fluid flow and how the flow pattern is in the whole caster. So once again, we have a lot of information in one single PhD. Why we need thermomechanical properties? Because again, the thermomechanical behavior depends on each steel grade, and the deformation of the process is very dependent on the process itself. But you know, sometimes it's not always the same, and cracking will occur when the total amount of deformation induced by the process will exceed the critical value of the steel. A steel is a steel, but the elements added to the steel, it makes it different materials. So here, a ball is a ball. But anyway, I would really not advise you to play tennis with a cricket ball or to play football with a basketball. We all know the consequences. I think most of us, we have tried. But why is so important in the process itself, where I am talking so much of the formation and thermomechanical properties? Because when the things go really, really wrong and the thing breaks out, so it's a breakout, it's only the tip of the iceberg. Because it breaks out when it really, really goes wrong. But it goes already bad when we have cracks. So first cracks, and then it breaks out. Luckily, breakouts are really a few on regular basis. Cracks, well, we have a little bit more than breakouts. But the cracking and solidification issues and all the things that we have behind, it's even more. But why? Steel is a material. So we could have material properties, just tensile tests. We could have thermomechanical properties. So we add temperature to that tensile test at different temperatures. And we could even have dynamic models, physical models, to measure not only temperature and strength, but also all the casting parameters associated to it. I will show you some examples how we have done it. So in the hot tensile test, so let's forget the normal tensile test because we are talking about thermomechanical. Temperature is very important on casting. So at room temperature, we cannot get that much information really. So it's better to do it already on temperature. There are several examples. We have the Sumitomo test, so also in-house method from Aachen University, and commercial Glibo machines. But also we have, for the dynamic test, we have mold simulators worldwide. There are several examples. We have the split chill tensile test in Leuven University. POSCO has a multi-mold simulator, so there's not only one, but there are 3 related mold simulators. And we do have in Tata Steel the Mould Cracking Simulator, which adds an extra, which is the cracking. But also there are some other tests that are very important for the secondary cooling region. So it's not such a high temperature, not during solidification, but they're extremely important. We have hot bending tests, torsion tests, and there could be even torsion tests on the glue itself. Together with Warwick, we are now exploring the hot bending test. Some examples of a hot tensile test. By the way, this is a steel dendrite of one of our steels. Long time ago, we have done some tests in Japan together with Sumitomo, hot tensile test with their in-house machine. What was our problem? We had one of our steels that it had way more cracking susceptibility than other 2 comparable steels. It was a very simple steel. It had really nothing. You could have a look at the composition here compared to the other 2. How does it look like the hot tensile test from Japan? It's a very nice device because it has it doesn't have any containment in the sample. So the semi-solid region, at least the liquid, is contained by an by a magnetic field, so an electromagnetic levitation field. And the sample is on a vertical direction and not in a horizontal direction like is on the other tests. That went wrong again. What do we have learned from these tests? Well, we could follow in this test the first ductility trough because it was so pure, there were no containments in it, so we could easily follow the first ductility trough. However, the collaboration unfortunately finished and we could not do more tests or more steels associated to that, so we left it there until another possibility comes. We kept looking further and we went back to China, to the University of Beijing, USTB. And we, together with them, it was explored and understood another method. The method is the opposite. What do you expect from a tensile test? On a tensile test, what you do is you have the sample and you heat it up. You put the sample on the machine, you heat it up, and then you pull it. In this case, it's the other way around. You first pull it, and you keep that tension constant. For example, you say, I'm going to pull it at, let's say, 1 megapascal. Yes? So you first pull it, keep it in tension, and then you heat it up. At the temperature at which sample with that exact fixed tension is going to break, that's the temperature associated for your hot ductility. So if you do that at different tensiles or different tensions, you guess it, you can also follow the ductility trough. So you could have the zero strength and zero ductility temperature in an opposite way. The mold cracking simulator. So going to the dynamic part of it. This is something we have at home, in-house. And what it does, it creates, oh, I think the videos are not working. So what it does, it creates a steel shell around it. It's a copper tube, which has a water-cooled copper tube. So it has exactly the same heat extraction conditions as a continuous caster mold. So once one has been submerged that in liquid steel, it creates a shell, and this half ring wedge, it's pulled outwards, and pulling, that's just created steel shell. With that outwards pulling, there is a load cell related to it, and it measures the force needed to pull it out. So that is obviously directly related to, if my work, so that is directly related to stress and strain curves. There is a model in between the test and the result test and the true stress, true strain, because that is related to the deformation or a tensile test of tubes. So it's not a simple flat sample, but there are tubes tensile tests as well. And we did use that mathematical approach to translate results from the mold cracking simulator to true stress, true strain. So what we have here is just very promising results, very important information of true stress, true strain of a steel that has been solidified under continuous casting conditions, and therefore it has the same microstructure and segregation, etc., as a continuous cast product. So I guess I'm just on time, but some conclusions. It's very important to select at least one method for each problem to tackle. I showed you several examples. It's not always possible to select one method where you could scan all temperature regions shown in or that appear in a continuous caster. So you have to select or to find out a way to understand the solidification range or the second ductility trough. And that really depends on your problem or the problem you want to tackle. Because for the modeling, for example, it's very crucial to have very good thermodynamic data. But the most challenging is if you don't have the data. You could, if your problem is the second ductility trough, I showed you, you don't really need it, not always a thermomechanical data. With thermodynamic data or thermodynamic simulations, to understand it is good enough. You could always improve it with tensile tests, or even what we are exploring now. That's a huge improvement I think is going to bring with a 3-point bending test. Well, it's 4-point bending test. But yeah, not all the available methods are needed, really. We need to select, and only what is necessary, and not really what's just nice to have. You know, budgets in any company is not unending, so you really need to focus, and that's the challenge, really. So with that, I would like to thank you all. And if you have any questions.
Thank you, Begonia, for such a wonderful talk. I hope to see some questions from our audience. Any questions to Begonia?
Or they understood everything or they don't understood a thing. So I hope the first one.
So, okay, I will ask one. When you mentioned about this boron, when you add it, right, you see the liquid surrounding the or near the grain boundaries surrounding grains. That could result in, cracking kind of thing. Did you observe any thing, such kind of composition in a confocal, either cooling slowly to see whether the liquid is reappearing after solidification?
No, not as directly, but it's a study done already. We knew already that when we started this study ourselves. We knew it's published already. It's done in. It was done by well, Sridhar itself did it in the US for a long time ago. So yes, they have seen exactly that. They have seen that it solidifies and suddenly remelts again.
Rangshin, yeah, please.
Hi, Satalena. It's a wonderful talk, very clear, very good. So I have a question. In one of your slides, you showed a phase field simulation of the dendrite at the beginning of the formation of the dendrite.
Yes.
I see the interface thickness is different at a different area.
This one, you mean?
No, it's somewhere else. You got a interface.
Oh no, that was not a simulation. This you mean?
Oh yes, you see.
That's not simulation. This is really EPMA measurements.
Okay. So measure the interface at the valley is thick than the tip, right?
Yes.
The red one. The next, the previous page. If you go to page 34, yeah.
Yes.
The 34, next one.
Yeah.
Yeah. You see at this between the diagram, the red area is thick.
Yeah.
Over there, and the tip is a thing. So
this is very schematic, of course, and what we wanted to explain here is that it's just not a direct from liquid to solid bulk, and this is what you get. You get a variation of it between dendrites. This is one dendrite, and you have some arms here of other dendrites.
Okay.
So you could see here a top dendrite, and probably this one is another dendrite here. So the difference between of them is what is the, yeah.
Okay, good. Thank you very much. Thank you.
Thank you.
Okay.
Ajitesh, you can ask your question directly if you want.
Oh, there was a question in the chat?
Yeah, in the chat by Ajitesh. Maybe I can read. For the mold step caster, how did you measure and gather data for segregation?
Well, first of all, what we did is we have been using it not for microsegregation yet. We use it for macrosegregation. So what we do is a line of overlapping OES PDA along the whole thickness of the sample to measure the macrosegregation along the mold, the sample of the wedge mold. But what Arunava has done, together with Katerina also here in our labs, is they have used each step of the mold wedge sample and they have measured the dendritic arm spacing from the surface until the center of each step. And that, there are several formulas in the literature that you can correlate the arm spacing with the solidification. so with the local cooling and etc. So that has been done as well. So indirectly, you could say the microsegregation is there, mostly the cooling that the microsegregation itself, but that has been done as well.
Okay, thank you.
Thank you.
Any more questions? No. Claire, you have anything?
No, just to say thank you very much. I particularly enjoyed the review of different techniques, because I think that's for many people listening, I think that was really informative, and it's already made me do some thinking. There's one of our research fellows who hasn't been able to attend, so I'll definitely point them towards the recording, because I think there's quite a few things in there that would be of particular interest, where he's working with Zushu, looking at, say, some of the residuals and for hot ductility issues. So some of the things you reviewed there, Begonia, was absolutely superb. So thank you very much indeed.
Thank you, thank you. And well, there are more techniques, so if he's interested, he could always contact me, of course. And indeed, there are a lot of techniques. It's just some of them are much more challenging than, let's say, not complicated, but much more challenging than others.
Yeah, it's interesting. We were just thinking about it yesterday. I was talking to Carl about some of these things, and sometimes it's about whether you need the data because you want to compare directly with, say, literature values and comparison, and sometimes it depends whether you want the mechanisms. And so just being able to unpick what are the critical factors, not just the holistic susceptibility. So which is why it's so good to see different approaches and then be able to do that critical assessment of which ones are the ones that are more appropriate to use. So no, really nice. And certainly I'll make sure that Mo's aware that the offer's there. So appreciate it. Thank you, Begonia.
Thank you very much. Thank you.
Oh, Michael, sorry, I need to leave. Okay. If no more questions, I once again thank you, Begonia, for your time and for wonderful talk. Thank you all for participating. Have a wonderful afternoon or evening. Bye-bye.
Thank you very much. Thank you for inviting me as well.
Thanks,
Thank you.
Begon. Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you.